called the bookstore, but nobody answered.
Yeah, there were some.
Somebody, I think Kareem said there was some on the Birmingham campus, but I hadn't been able to.
I know they have some in there. Well, I didn't get it. She said I had zero balance on my account. Then I went to financial aid. She said I had $510. I'm like, I gotta go talk to them in the morning.
So chapter 7, what is chapter 7? Logic gate. I'll get you on that. So here we're going to deal with logic, right? Drive combinational and sequential logic circuits, create PLC ladder diagrams, create PLC ladder diagram programs for not, and, or, and, nor, exclusive ors and exclusive nors. And we're not going to get into too much into this. We'll look at truth tables. We use Boolean algebra and also something called Karloff math to have us, that's what engineers do, to reduce circuits. And we're not going to really get into that this term. We get into that a lot more if you're in the industrial electronics and you take digital. So we're not going to use a logic converter, and we're not going to convert Boolean expressions, even though we'll look at them. And we're not going to convert a ladder logic diagram into Boolean expressions. We're not going to do that. So what we have is we have what we call the 5 basic logic gates. Anybody know what the 5 basic logic gates are? Not. Okay. Yeah. There's stapling. There it is over there. Then we get into combinational logic circuits, and the book is kind of misleading with. This is where we get our most more advanced. So we have the basic logic gates, and I don't know why they didn't pop up first, guys. We have the basic logic gates, which are what? Oops. I can just write it. And by the way, when you deal with logic, you capitalize everything, so you don't. So this would be and. I wouldn't write it as lowercase and because that's the word and, right? Understand that? So we got and, we got or, we got nan, we got nor, we got not. Those are 5 basic logic gates. And we call these the basic logic gates. Then we run into what we call combinational logic. Combinational logic, the book's got this kind of wrong, is when we use these 5 basic logic gates to create circuits that perform more advanced functions. So like exclusive or, exclusive nors, these are combinational logic. Timers, counters, decoders, encoders, multiplexers, demultiplexers, shift registers, and we got this can go on and on. But all these are made of the 5 basic gates, believe that or not. So all we do is they start combining these 5 basic logic gates. And we call them gates because we have inputs and we have outputs. And the way a lot of people think about them is opening and closing the gate to let something either come out of the output or close the output off, right? You understand that? So that's got its name. PLCs, we don't really have the gates, we have the instructions, right? You understand that simulates the physical logic. So there they are, the 5 basic logic gates, not and, or, and, nor. And combinational that we're going to study here, exclusive ors and exclusive nors. Now, we're going to implement these in this class. We're going to implement these with contacts. But if you get into, if you take advanced PLCs, you find we can implement these with instructions that stand by themselves. So we're going to learn how to wire these in using contact. Everybody okay? Even exclusive or inclusive mode. So we'll use some combination of logic. If I was going to do this in digital, this would be made up of several circuits, several gates inside a single integrated circuit. Sequential logics have outputs that depends on their inputs that are timed. These are synchronous devices. So they depend on clock pulses. So their outputs change relative to inputs, but then it's also timed. Does that make sense? So the inputs can change, but they don't respond to the change in inputs until we have a clock pulse. And digital logic, these are JK plus clock. So we control the Q and the not Q output. So this is not Q and not Q output by the state that we put on the J and K. But it doesn't change until we have a clock pulse. This is actual clock symbol. The little triangle means it's a clock, and the bubble means that it's timed on the falling edge. So what that means is that this guy is looking for this guy right here. It's not looking for that guy. It's looking for what? That guy. So that little guy right here means this is a clock input. And the little bubble means on the falling edge. If you don't have the bubble, then it would be what? Rising edge, basically. So the way this guy works, if I was to put a 1 on the K and if I was to put a 1 on a J and 0, y'all don't need to know this. Is just, it's going to sit there now in the doomsday. Because I don't have a what? I don't have a pulse. So as soon as that clock input does that, then the Q would go to 1 and the not Q would go to 0. And then I could swap them around. So if I put a 1, 0, what do you think would happen? Nothing until I have what? Until I have this, right, on the input. And then they would swap states. And if I come up here and do this, then every clock pulse, the output would toggle. So they would swap positions. So we use these guys for counters, but this is synchronous, right? This is sequential logic. In other words, I can put 1s and 0s on the inputs, but they don't change until what? The outputs don't change until we have a clock pulse. And this is sequential logic. We call it synchronous. So we have one shot. We have edge detectors on our PLC that we're looking at. Every gate logic has a Boolean expression so Boolean algebra. We call it Boolean algebra. This is not regular algebra. This is Boolean algebra. All we have in here is ands and ors, and nands and nors. And what we do is we use multiplication symbols. So in Boolean algebra, I wouldn't say A times B, I would say A and B. So that right there tells me I'm doing what? An and. So you got to understand, this right here is a symbol. Now you learned it to mean what? Multiply, but it's a symbol. And what's a symbol? A symbol is something that stands for something else. So in Boolean algebra, that symbol stands for what? And. All are ands. So if I came up here and did this, that would be and. Or if I came over here and did this, that would be and. Or if I just put the two letters together, that would be an and. So everything that we learn in math for multiplication in Boolean algebra, it's what? It's for an and operation. We use a plus for an or. So we wouldn't say A plus B plus C in Boolean algebra. We would say A or B or C. That makes sense? So Boolean algebra, and then there's a lot of reduction that we learn that you're going to learn in algebra that kind of applies. We don't have squares. We don't have square roots. So if I had A and A, yeah, that's going to equal to A. It's not going to equal to A squared. That's not plus. This is Boolean algebra.
Okay, what again?
It's or.
Or, okay.
So in Boolean algebra, this symbol right here indicates or. And then if I put a bar above it, this would tell us it's a NAND. So if I put a bar above this, then this would be a NOR. But that's what we would do. So Boolean algebra, what we can do is we can mathematically represent a digital circuit. And then what we can do is we can mathematically reduce it. So if we got like terms, we could rearrange them. We could use the laws of combination and all those other laws that you learn to reduce equations. But it's a little different. So if I can take a big long, if I can develop an equation for the circuit and then I can reduce it, that means that circuit's going to do the same thing, but it's going to have less parts, right? You understand? This really came into play with me when I was at US Steel. They bought a scale, an electric scale for the line scale over there, and they didn't buy it with an auto zero circuit. And it's a truck scale. So what happens with a truck scale? Well, it's constantly got garbage on it, right? Understand? And so what you do is you come up with a way that you will zero the scale out if there's no motion on the scale. If a truck's not pulling on the scale, you zero it every once in a while to make an accurate reading, right? And I thought I was having to look at all these digits. And then I took it in front of my boss and said, well, let's set up an equation for it. And set up an equation for it. And it was unbelievable how far it would reduce. So, you know, I was going to use a circuit card this big, and it came up to be just a little old tiny thing because we were able to reduce the circuit. So Boolean algebra is very, very powerful. And like I said, you'll deal with that more in digital. We have what we call true states, true and falses. So in this one, what we're going to say, the rung is true. Now, the rung is true means we're going to be able to energize whatever the output instruction is, right? You understand? If you say the rung is false, it means the output instruction is going to be de-energized or it's going to be false, right? You understand that? So we use ones in the Boolean algebra, or I'm sorry, when we actually put values into the Boolean algebra equation, we use ones to indicate ones and zeros to indicate one, zero. Okay? That makes sense. But here we're going to use voltages. So we call them logic highs, represented by the presence of a voltage potential. Now inside the PLC, they use what they call TTL voltage level, which is 5 volts. So 5 volts would represent a high, or something around 5 volts. You can't say 5 volts because our voltage is very good. It's actually 2.4 volts up to around 7 volts to consider a little high on an input. Now on PLCs, it's what we put on our now. So inside the PLC, we're going to deal with digital voltage levels. On our input and output ports, we're going to deal with other voltage levels, right? And they could be just about anything. But if the voltage is on the input, we're going to say it's a 1, or we're going to say it's a 1, right? If the voltage is not on it, we're going to say it's what? 0. And there's all types of voltages out in plants. And instead of me trying to put something in there to generate it, a lot of times we can buy a PLC that uses those inputs. If I got 240 volt AC, I guarantee you can find a PLC that's got 240 volt AC in it. Not much in new installation, but in older installation. Most of our inputs now are DC, and most of them are 24 volts. So 24 volts, we would call that a high, right? You understand? Or a 1. And then 0 volts is true whether we're using AC or DC. So if I put 0 volts on one of my input modules, then it's going to be what? It's going to be a false, or what we call binary 0. That makes sense? Everybody okay? Pretty straightforward. So what we have is we have a truth table. The book don't get this right. What a truth table is a chart that indicates how the output of a digital circuit. So normally when we do this, now these are generic. In real life, these signals are going to have names. But when we teach digital, we usually make the inputs generic. So I might come over here and have an AND gate. So this is the symbol for an AND gate, by the way. So it's the shape of a D.
And then this would be 2 inputs. And I could call these inputs anything, but I might, normally what we do generically is your inputs are going to be your low letters of your alphabet. And your outputs are usually going to be your high letters of your alphabet. And that's just generic. So most books teach that. But if you just actually look at a digital logic circuit, these guys have names, right? You understand? These signals have names. You understand that? I can show y'all a true digital print. If I can, what would they do that? So these are names. So when we teach digital, we use like A, B, C, D, E, F, like that for the inputs to do a truth table. But in real life, these signals are going to have what? Names. And most of the time, the names make sense. Like that way you think that would be ready, reset, yeah. And then these are Q outputs. But these, now anywhere that you go, you know those are what? Those are the same. That makes sense. On a true print, the signals are going to have names. Most of the time, they're going to be what we refer to as mnemonics. So clock 88, that's going to be a digital clock, right? See that? Here's the address bus. Here's the data bus. This is the actual CPU card. And then these are just basic logic gates, right? So this is an and that's an AND. This is an inverter, but you look at the bubbles on the wrong side. So generically, when we teach digital, what we do is we just use A, B, C. We use the lower cases of the alphabet, the lower letters of the alphabet for our input, and the upper cases as our output. So what you do is you put your inputs on the left, and you put your output on the right. So this circuit right here, the input, we have 3 inputs. So how many combinations do we have when we put on those 3 inputs? 2 to the third. 2 to the third, right? It should be what? 8. And there they are. 1, 2, 3, 4, 5, 6, 7, 8. That's every combination I could possibly put on. That's all you have to do. So what a truth table does, it shows you how the output responds to every possible combination you could put on the input. So what you do is you just start counting. So if I had 4 inputs, then I could put 16, right? Right? You understand that? Right? If I had 5, I could put 32, and after that, truth table reduces. That's when you use Boolean algebra instead. Because, you get so many entries in the truth table. I got 8 inputs, every 256 combinations of inputs, and I would have to count through every one of them, right? You understand? So there's binary 0, 1, 2, 3, 4, 5, 6, 7. I can't count any 4, so that's all my combinations. So what this is saying is this combination right here gives me a what? A 1. Now if we're going to write the Boolean equation for the circuit, and we're not going to reduce it, the actual equation is I would come over here and say Y, that's my what, that's my output, and I would write this down right here. So I'd say A, B, C. The ones that were zeros, I would put bar above them. The ones that wasn't zeros, I wouldn't put bars above them. And then I would come down here and find my next combination. And I'd say OR, because that's true, right? Or, what would I put here? I'd put A, and then I would put what? B, C. Then I would say OR, and then I would come down here. And then I'd put A, B, not C. And then my last one, I would put A, B, C. So that's the equation for the circuit. And now I can come in and I can put ones and zeros in there. And then I can come in that equation, or I can do what? I can see if it would reduce. And it does. So if I was to go through all the math, it comes up and this is the actual final thing. So up here, I've got an OR gate that's got 4 inputs on it. 3 inputs. I've got inverters and all kind of circuits, but this is what it reduces. So that's the power of Boolean algebra. And this should have he's using the asterisk for that, but it's actually, in Boolean algebra, you put a asterisk. So that's the equation. And then this right here would actually be the circuit that you implement. So this is the symbol of an AND gate. This is the symbol of an OR gate. This is a symbol for an inverter. This would be the actual circuit that would replace the one that I had, which would be very complicated. So once we've got an equation, the first thing we do is just like in math, y'all got to take, if you're in the degree program, everybody's got to take algebra. What's one of the main things they teach you to do? Reduce equations, right? Get all those A, B, and C. When I was in high school, I didn't do really well in math. But then when I got in the military and I saw a use for it, I aced every math class I ever took because now the math had what? Had reasons. We weren't actually solving for A. We were solving for an equation and it reduced the size of the circle. Are we okay? So these are symbols. What's this a symbol for? And. This is a symbol for OR. And this is a symbol for OR. This guy has 2 names. You're right. The circuit's called an inverter, but the logic is called not. Yeah. So the logic it does is called a not. So you say not A. So if A is not A. So if A is a 1, this would be not A, which would be what? A 0. If this was a 0, this would be not A, this would be what? A 1. So that's the only logic gate that's got 2 names to it. The logic function is called a not. So if you get into advanced PLCs, we're not going to call it an inverter, right? We're going to call it according to the logic function that it performs. So the logic it performs is a not. This is called an and it's an and logic. This is an and this is an. Now these are ANSI symbols. You know what ANSI stands for? What do you think the A stands for? American National Standard Institute. Yeah. So PLCs don't use it. They use the IEC, the International Electrotechnical Council, which is an international standard. And we'll show you other symbols too. So we can program, it's called function block programming. We can write PLC programs using symbols. It's called function block programming. But they use the international symbols. They don't use the ANSI symbols. Every PLC I've ever seen. So the book teaches the ANSI, American National Standard Institute, by the way. This is a symbol for a not logic or inverter, right? Okay. This would be the truth table. So if A is a 0, Y is a 1. If A is a 1, Y is a 0. So it's only got 1 input. So how many combinations do we have? We have 2 to the first, right? Which gives us 2 combinations. This is an AND. 2 input AND logic gate symbol is Boolean expression. So here's the Boolean expression right here. Did they give us the Boolean expression for the not? It's kind of weird. Yeah. So Y equals what? Not A. The Boolean expression is the way we would create a math. This gives people problems too, because they want to put the output on the right because that's the way it is. But it's a Boolean equation. What you solve for is on the left, right? On any math equation. So what we're doing is we're solving for the output. So in a Boolean equation, the output goes on the left. but on the symbol, the output is on the wall. Right. And I see that all the time when I do digital. Somebody will do it wrong. They'll say A and B equals Y. And that's wrong. That's mathematically wrong. Because what you're solving for is on the Y. On the left on any math equation. So this is wrong. I guarantee you, you take digital tomorrow. Now an AND gate can have at least what? 2. Now look what happens here. So what we do, so what we're going to do is when we see this D symbol, we're going to use the term all. So here we'll say all highs on the inputs equals a high on the output. Or most people just say all highs equals high. So let's see if that's true. So is this all highs? No, the output is low. Right. Is this all high? Right. Is this all high? Is this all high? Yes. And the output's a 1. Make sense? In PLCs, we're going to say true is equal to true. All true, all inputs, all true inputs is going to equal a true on the output. Make sense? Because we're not going to have highs and we're not going to have lows. We're writing a program that's inside a computer, right? Well, got to have at least 2 inputs. How many inputs could we have? The maximum I've seen is 12. In PLCs, as many as you want. But it still says all highs equal a high. It's just that here, you know, if I got a 12 input AND gate, that would be 4,096 entries in my true table, which is nice to know, but I could go through it all day long, but the output would only go true when all the inputs were what? True. No matter how many inputs you got, right? You understand? So to get an AND gate, you got to have a minimum of what? 2. There's no such thing as a 1 input AND gate. So this is an OR gate. So when we see this shape like this, we're going to use the term any. High on A input equals, I'm going to put the equal signs, equals a high on the output. So is this any high? No. So the output's what? Not high. Is this any high? Is this any high? Is this any high? Now some people want to say all, but AND gates are going to have one unique output. So look at the truth table. Why don't we call this all? Because it's not a unique output, right? Because I have, of the 4 combinations I can put on that, 3 of them gives me a high. Or a 1, right? You understand? But some people will say that. They'll call this all, but that's not true. Because if it was all, this would be the only combination that would give me the 1. Right? You understand that? Mm-hmm. So here we would say any true gives me a true. How many inputs can we put on an OR gate? Minimum of 2. Minimum of 2. Now they'll butterfly these things out. They don't. Some people draw them real big, but what they'll usually do is come up here and do this. And then they'll put the symbol right there and they'll just bring the inputs in like that if they want to go. So that's OR. We can do this with context. So how would you think we would do an AND with context? with inputs. So I got L1 and I got L2. Here I got an output over here. Right. So what we're trying to do is we're going to say all truths to get a true, right? Before the output goes true. And here we'd say enter time. How would we hook our contact? In series, right? And how many of them could I put? At least two. That's the point right there. Minimum of two. And we'll just call these A, B, C, D, and E. Of course, we'd have to say an L. So A would have to be closed. B would have to be closed. C would have to be closed. All of them would have to be closed. All of them would have to be true before the run went true, right? That makes sense. So this is an AND. This is the way we do an AND with relay. Relay logic has been around for years. This is the way we do it. So this is AND logic with nothing but contacts. Are we okay? So how would we do an OR? Parallel, yeah. So here's L2. This would be my coil instruction or my output instruction. And then I would come over here and I would just put my contacts in parallel. I'm not going to do as many. I'm just going to do 3. Is that okay? Now this is the A, B, C. So A, B, and C would have to be true, right? You understand? Or they would close before what? Before the output became true, the run became true. You understand that? So normally open contacts in parallel, these are OR. This is an OR. Normally open contacts in series is an AND. So this is a NAND. NAND says all highs to get a low. I'm going to say, so all highs on the input equals a low on the output, right? Oops. So we're going to abbreviate it a little bit. All highs equal a low. So we look, is this all highs? All highs equal a low, so it's not, right? You understand? So these are false, so this is false. This all highs. Okay, so this is what? False. This all highs. No. All highs equal to what? Low. Everybody okay? All highs equal to low. So how are we going to implement this guy with contacts?
Would be contacts in series.
Well, how would this be all? So people, and this is the problem we have, they see this and they think series contacts are ANDs, and that's not true. This would be an AND right here. Now what you got to understand is so what I'm doing out here is, and to understand this, let's just use 2 so you can understand it. Is we're controlling these with normally open push buttons. So what I'll do is I'm going to come over here on my PLC. So what we're over here on my input port, and let's and we'll just use 2. So let's come over here and do it this way. So I'm going to come up here and I'm going to put a push button I'm going to call A. And then I'm going to come over here and put a relay coil over there. And then I'm gonna come over here, I'm gonna put a push button called B. And I'm gonna put another relay coil over here. And I'm just gonna call this 1 and 2. I'll call this B. And then what I'm gonna do is I'm gonna come over here, and then I'm gonna come over and do this. So this is my outlet there. And this is gonna be 1, and this is gonna be 2. So when I press that button up there, when I press that button A, is the output going to be true? Is it going to be on or is it going to be off? So on NANDs and NORs, we're looking for what's going to make the rung false. So ANDs and ORs, we're looking for what makes the rung true. For NANDs and NORs, we're looking what makes the rung false. So if my output energizes, we say the rung is true. If I'm going to press switch 1, that's going to open this contact right here, right?
Mhm.
It's going to turn off.
Yeah.
No. I'm going to press B by itself. That's going to open this one. Is the rung going to turn off? What do I have to do to turn this on? I have to make A and B through, right? Understand? Turn the rung on. So what we do for ANDs and what we do for NANDs is we normally use examine if open. Now, this isn't a stop circuit. This is logic. So my input I would use for all my logic. I'm going to normally open push button on my PLC. Every one of them normally open push button. So what we're doing here is we're using examine open, right? So I have to press both of them. We're using the examine open. So when I press them, they go false, right? Make sense? So relay normally closed contacts, examine open contacts in parallel. This makes what we call a NAND. Now the problem is people learn this. And this happens in every class I've ever taught. And they think if they see for some reason if they see contacts in series, they think ANDs and NANDs, but that's false. So normally open contacts in series, right, is an AND. Normally closed contact, did I say it right? Normally closed contact in parallel is an AND. Everybody okay?
Mhm.
We'll see who does this on the next test. Because this is what you're going to have to examine. So how many could I put in parallel though? As many as you need. So we got to have to get a NAND. We got to have a minimum of what? 2. A maximum of whatever we can do, right? So this is a NOR. It says any high equals a low. So any input high would mean the output would go false, right? You understand that? So this is where we're going to use what? In series, yeah. Are we okay? Now these contacts are going to be controlled by something, right? Don't understand that. That's our basic gauge. Nope, I'm sorry. I forgot one, which is the important. Did they show that? Oh, the not. Everybody okay on the not? How do we implement a not? One normally closed contact. One. Oops. So this is not. And this guy right here does no logic. That's not one of the buttons. That's not one. So normally open contact does no logic. It don't invert, it don't and, it don't or, it don't do anything, right? So one normally open contact, if it's in there by itself, it does no logic. One normally closed contact in there by itself is a what? Is a not. As soon as I put two, it's no longer a not. Yeah, this is another one. Right? There's a simulation program out there called Logic Pro. And you can get a permanent license on it. It's about $45. It's a really neat application, very similar to RS Logic 500. You can't run them. They're not compatible with so if you create this program, you can't download it into a PLC. This is a simulation. So this is an IO simulator. It's actually got it's got one, two, three input modules. One is hooked up to the protocol phone system. And it's got 1, 2, 3 outputs. These are hooked up to 7 segment display. We can display I'm sorry, 0 to 9. You can change your inputs by just right clicking on them. So right now I'm going to use switches, and that would be a what? Push button. Normally open, normally close. So this would be a limit switch, and that's your option. Over here you can change the color of the lights. You got 3 different colors you can make them. So right now we're using these first 3 switches, and right now they're all false, right? So we'll come up here and we'll download this. We go online. And this is a little different, so we download it from over here, and then we switch it to run. And notice some of the LEDs, some of the lights came off right off the bat. So right now here's so 0. I've got switch 1 is hooked up to input 1/1/0. 1 switch 2 is 1/1, and then switch 3 is 1/2. Notice right now they're all false, right? So if I was to look at my IO map, it would be all zeros in there. So that's what we're looking at, is that IO map that tells us what's true and what's false. Everybody okay? So how am I going to make this output go true? Well, I close that one, it's still not true, right? You understand? Because it's a what? It's an and, right? You understand? So all my inputs have to be true before my what? Before my output. So you can't look at it from a contact point of view. You got to look at it from what's controlling that. So if I was to look at my IO map in my project tree, a 1 is what? A true. Everybody okay? Now what's this one below it? This is an O. So notice, as soon as I close, and this says any. So if any input is true, then the rung is going to be true, right? So there I close that one. This is not true because this is an and, but this went true instantly, right? Understand that? I'm going to close this one. I'm going to close this one. I'm going to open this one. I can open that one. I can open that one now. None of them's true. So if any input is true, right, or if I got a 1 in my input table, then this output would be what? True. That makes sense? Now there's a not. I got it hooked up to switch 0. So my input is false, my output is true, right? My input is true, my output is false. So there's a not. Let's see which one I'm on. Yes or no? This is a NAND. I'm sorry, yeah. This is an AND. And now when we get to NAND, we're trying to see what makes the rung false, right? You understand? So ANDs and ORs, we're seeing what makes the rung true, right? You understand that? NANDs and NORs is what makes the rung what? False. Everybody understand that? So I'm going to come here and flip the switch. Is the rung false? No. I'm going to come here, I'm going to open that switch, I'm going to flip this switch. Is the rung false? No. I'm going to flip this switch. Is the rung false? When's it going to go false? When all of them are true, right? So when all of them are true, the output went what? False. This is a NAND. As soon as I say all, I know it's got to be either what? An AND or an AND. An AND is what's required to make the rung go true. A NAND is what's required to make the rung go false. And then this is, we're down to this guy right here. This rung's false already. So this is a NOR. So I close any one of them. Any one of them causes the rung to go what? False. Then we get to these weird guys down here. So let's talk about that. We constantly need to compare things. Of course, here in digital, we're only comparing 2 things, right? You know what I'm saying? When you get in, if you take advanced PLC, we can work with words. We can compare 2 words. But with contacts and exclusive OR gates themselves, we're going to compare 2 things. So what do we do when we compare? What's the 2 things we know when we compare 2 things? I mean, numbers. I'm sorry. What are we looking for? I'm listening. Yeah, but what are we trying, when we compare, when you compare 2 things, what are you looking for when you compare things? See if they're the same or see if they're what? Different. That's exclusive OR. There are comparators. They're going to tell us if the inputs are the same, and they're going to indicate if the inputs are different. They're going to give us some indication. So the rung is either going to go true when they're the same, or it's going to go false when they're the same, right? Depending on which one we got. So here's our comparators, and all we're doing is comparing 2 different things to see they're what? If they're equal or not equal, or if they're the same or not the same, since we're only doing two inputs. So this is the digital symbol for an exclusive OR. Right here. This is an exclusive OR. So it looks like an OR, but it's got this shadow right here, right? So this is not an OR. this guy here, and we'll always have two in. Two. All right, understand that. So here we're going to use switch 0 and 1. It's only two switches. Now, what the output does is show you what we get when they're not equal. So this says if they're not equal, the output will be true. It will be high. They're not equal. So if they're not equal, the output will be high. Then they're equal, we should expect the output to do what? Should go false, yeah. So the inputs are not equal. So you see, this is what happens. So here they're equal, right? You understand? And we get a what? A false. Here they're equal, we get a false. Here they're not equal, we get true. Understand? We use this, so we were trying to figure out something on our PLC. And then this right here is an exclusive NOR. This is the symbol. So this says what we get when they're what? Not equal, right? So it says if they're not equal, we're going to get a 0. So here they're not equal, right? And what do we get? We get a false. When they are equal, we get a what? True. So let's see how we implement exclusive ORs and exclusive NORs with two contacts. So this is an exclusive NOR. This is an exclusive OR. You see I'm using the same contacts twice. So here I'm using a normally open, examine it closed, right? You understand? Down here I'm using a what? Examine it closed. Same input, right? Here this is examine it open, this is examine. So I'm only using input 0 and 1. So this is an exclusive NOR. But when they're not equal, we should have a what? A 0. When they are equal, we should have a 1. So let's go up here. So I'm just using these. Here they are equal. What do I get? I might have this backwards. I think I do. So here they're not equal, right? So here they're equal, we get a what? Here they're not equal, we get a what? Here they're equal, we get a what? False. So they're labeled backwards, right? Are you okay? Understand? Yes or no?
Sure.
So this is an exclusive NOR right here. Exclusive, and this is the way we abbreviate it. The actual whole thing is exclusive, right? And this would be NOR. But we abbreviate that as an X NOR. So this is the abbreviation. So the symbol shows us what we get when they are not equal. So according to this, if they're not equal, we should get a what? False. If they are equal, we should get a what? True. Now when we say true, we're talking about the output will be energized. So if they're not equal, right, you understand, we should get a what? A de-energized, right? If they are equal, we should get a what? Energized. So it looks like these are labeled backwards. So here they're equal, right? So 0 and 1 are equal, so they're equal on this side and equal on that side, right? So it's labeled as a what? No. Is that right? Huh? Yeah. Yeah, so this is the symbol we're looking at. I think when I just showed about that, it looks like it's yellow. I might not. Yeah. Most people like to put them on the table. So what this bubble tells us, this tells us what we get for what. Not equal. So how many combinations can I put on this? 4. And that's a normal tendency. People see 2 inputs and they say, well, you can only put 2 combinations. But every legal combination, so what we do is we count the number of inputs and you raise 2 to that power. So 2 to 2 inputs. So this is how many combinations we can put on this input, right? We put 4 combinations. So I'll just start counting. I put 0, 1, 2, and 3. Now I'm running out of combinations, right? So over here, let's just put true. So this says we get a 0 if they're not equal. So this right here would be false, right? This right here would be what? False. And then we get a 1. That means if my 2 inputs are up, or if my 2 inputs are up, or my 2 inputs are down, right? You understand that? You should get a what? So my two inputs are up, or is it true? Yeah. No, so it's labeled backwards. Oops, I'm gonna go through right here. So exclusive or, right? Everybody okay? This down here, see my 2 inputs are what? Equal, and it's what? True. Here they're not equal, it's what? False. Here they're equal, it's what? True. Here they're not equal, it's what? False. Up here, they're equal, it's what? True. I'm sorry, they're not equal. Here they're equal, it's what? False, right? Here they're not equal, it's what? True. Here they're equal, it's what? False. Here there's not equal, it's true. So it depends on what you're looking for when it's true, right? Does that make sense? So if you need a false when they're true, you're going to use a what? You're going to use an exclusive NOR. This is not the symbol, right? Nobody called me out on that. So if you need a false when they're true, when the two inputs are true, then you're supposed to NOR, right? If you need a true when the true, the two inputs are the same, then you use a loss. NOR. These are called combinational logic because it consists of local law. This consists of a method and a not. So that's fine. This is pretty easy. So this is no. This is a little harder to see. So there's our 5 logics that we can wire with what? We can wire with relays. You can also see up in the palette, so we got and, ors, exclusive ors, nots, clears, so that's all the logic. Well, then we got counters and timers and other kind of stuff, that's software, right? But if you take digital, if you take digital, if you're in industrial electronics, you know, digital is one of your core classes, then you'll see how we can make counters and time, we can make just about anything out of the 5 basic gates. Here, these are all programmed in, right? Y'all got any questions? So let's see what else is on this PowerPoint. I think that's it. Here's the IEC symbol, the International Electrotechnical Council. And here's their symbol. So this is what they're going to do. If you ever get into a PLC, you program it in what we call function block programming. Then we'll use these symbols right here. And then we have symbols for timers, we have symbols for counters. And what you find out is used to when they first came out with PLCs, everything was coils. All your timers and everything was coil. But what they've done over time is they kind of combined the ladder language with the function block programming language. So the symbol for a timer would be exactly the same in ladder than it would be in function block programming. So they kind of cross over on some of your advanced instructions. This should be up there, by the way. So if you did programming in that, then that's what it would look like. In fact, I did a So how would you think we would do this? So I'd say Y, then we can move things around, so I can say B, right? Then I can say or EB. Then I'll just put everything out there, not A or CB. And then I would pull the B out, so I'd say Y would be equal to B1, because I pulled the B out, or E, or not A or CD. And then I know anything word with a 1 is a 1. So that would be a 1, so I'd come up and then we come up, so this would reduce down to this right here. So we got rid of an input, just like that. Less circuitry, right? You're not required to know how to do that, but you can see the power of it. Once we establish a formula, a Boolean equation for a circuit, then we start looking for like terms. We combine them, and then we have some rules that we follow. That's a little different than in algebra. So A and A is not A squared, it's A. B or B is not B or B is B, right? And you can do stuff like that. And this is what they're talking. It's trying to make logic gates with different Boolean equations, but we're not going to look at that. So they're taking a Boolean equation and actually creating a ladder diagram. We're not gonna have to do that in this class. And so that's it for logic. So you probably need to know what the symbols, right?
Yeah.
For the logic gates. And then probably be able to identify the truth tables. If you know, do that. Be okay there? And then how we wire contacts to get what? Nots, and, ors, nands, and ors, and then exclusive ors and exclusive nors. Please go to lab, but let me go back here. This guy, this is the learning pit. And guys, this is about the only option you got if you're behind on labs. You're more than welcome to get this software and work on these at home. You can save them on the thumb drive and you can run it on and check them off that way. That's about the only option you have in this class because there's going to be no time to make up labs. Now we could probably arrange for the lab to be open, but y'all gonna have to make sure somebody's here. It's just that you can't get your circuit signed off. You'll have to bring them in and show them.
So I think we mental lab?
Yeah, that would be the only option. Get this software package and save it on the thumb drive and bring it in. Or try to get the lab open. Because I can't come over here. I'm on the I want to show you this. What I did is I put these are the 5 languages that's available for programming in PLCs. And of course, the most widely used is ladder, which is what we're learning. Structured text, function block, diagram, sequential logic chart, and then instructions. And what they're trying to do is they're trying to come up with a method. People coming up through different disciplines could learn programming PLCs really easy. Structured text is kind of like Pascal, if y'all ever programmed Pascal. So this is a structured text program. This is not for a PLC, it's for a little microcontroller called an Arduino, which is basically the same thing. This is something that I'm into. Look, you gotta learn all this stuff. You gotta learn syntax and all this kind of stuff. But if you were a computer programmer, you came up with these programming languages like Pascal and Java and Visual Basic and stuff like that, you'd jump in on this stuff. Then we have what we call function block programming. And that's function block programming up there. So you just use what? Symbols. Now, so there's and, right? I'll do that. And then we have these symbols right. These are still the same look in advanced programming. There's some symbols that's the same in both function block programming and ladder. So just about all the PLC programming languages out for your high level commands, they use blocks. They don't use coils. But if you get into step 7, which is the older version of Siemens programming software, they use coils for it. So this would be people that come up through digital and stuff like that, or electronics. This is sequential function chart programming, which is pretty neat. And this is really cool. So what you do is you set up a sequential chart, and you have steps, and then you put what's required to go between each step. So these are steps, by the way. And then this says you what output it generates, which is pretty neat. And then you compile this over, and it will create the program for you. When you take AEC 208, which is in both degrees, we'll look at these and then we'll look at. In fact, this is one of Siemens' sequential function charts too. This is instruction step with it. This is a lot like the old assembly language that I first learned. So you use a lot of mnemonics over here to represent instructions. And what they did on this example is they showed you the actual instructionless program that would represent this program. I'm so glad you're learning ladder. And then, of course, this is what we're learning, ladder diagrams, which are very similar between just about every PLC that I've ever dealt with. So this is familiar, right? Okay. I hope so. And this is the actual,
Probably bonus question on the test, wasn't it?
I think it might have been. I know there's a bonus question on there. And I've redid the rules. And this is kind of different in the book. What am I requiring of y'all? To actually draw the actual power supplies themselves, right?
Yeah.
Now, if you're working with the Micrologic 1000, that's a little secret sequence. Then what you're going to do is you're going to put, and we're using syncing inputs. But on your over here, you're going to put that's in the SAC. So on ours, on the 1000s, you have AC outputs, 120 volts. I told y'all to keep the cover closed, right? On the 1100s, which we're trying to go all the way over to the 1000s or 1100s. So, the 504s are very, very they're slow. Not the PLCs themselves are not slow. It's the interface between the PLC and the computer. So what happens? You come over here and you flip a switch, and the light turns on instantly. And 2 seconds later, it lights up on your screen saying that it's true. So it's just that 1200 bits per second that it's trying to communicate. And it's a lot easier to configure. Let's see. I also put this in there. This demonstrates how the thing scans, right? So what does it do? Does one rung at a time, starts on L1 side, scans it into it, runs the logic, updates the output, and then it goes all the way down to the end instruction to tell you about the stuff. We talked about the project tree. Everybody okay? That some of y'all had problems with that on the test. System files we don't have access to. And these are our, this is what I wanted to also bring up. It depends on the PLC you got. So normally inputs and outputs, this depends on how many inputs outputs you got. These are assigned by the PLC. Your timers, it depends on whether you got a fixed PLC or whether you got a modular PLC, how many timers you can have. By default, they're going to be called T4. But some Allen-Bradley PLCs allow file numbers 9 to 255 to be assigned to that file above one. Yes, too. So I might look at a PLC, and they might have T, which means it's a watt.
Okay.
It's a timer, but then they might have T99. So just because the book says it's always T4, it basically depends on the PLC that you're using. If you're on one of the little 1100s, you can assign them anything you want to. By default, it's going to do T4s, but you can do you can assign them any of those. So your counters, you can get, by default, you're going to keep C5, which you can use if you can read the PLC, and basically. When you get your manual, and we have the manual for all these PLCs up there up on Blackboard. And where would y'all think they would be at? Reference material. I did the wrong key. So inside course content, and then over here, reference material. And then Allen Bradley PLC manuals, MicroLogic 1100. This is the instruction set. I understand what's an instruction. Shows you all the instructions that this PLC can handle, right? So this is the instruction set manual. And then controller memory. So we got T right here, and it's going to use what? Data file what? 4. But down here it says we can assign it any number between what? 9 and 255. 255, yeah. It's an 8-bit. Are we okay? And then the input data files, these are assigned according to how many inputs you have. So the 1100 has 10 inputs, and it's got 6 outputs. I think that's the same on the mic. This guy here has 16 inputs and 16 outputs, but they only give you how many switches. Now what they did give us is these terminal boards down here. So we understood these things, we could wire up all 16 down there. So this book is gonna teach T4 is for timers, T5 is for counters, R6 is for control registers, N7 is for integers, and F8 is for floating points. But most of your PLCs give you the ability to expand that, right? But these first 9 are reserved. These you can assign. It's just that if you assign 9 to bit files, then you can't use what? 9 per time, right? That makes sense? But you have to manage this. We'll find out when we get to Siemens PLC, you manage all of them. So you got to get used to that. You can't assign 2 things to the same memory block. These right here would be, these guys here you have no problems with because these are built into the PLC. T4 is built for what? Timers. You can't assign anything else to data file 4. You can't assign anything to data file 4. Okay, anything else I wanted to bring up? That's about it. This is the syntax, and this was, I'm trying to do it on the review. So this is the syntax, right? So we start off, X is going to be what? No, X is going to be D is going to be the file number. Right? Yeah. Now, if we got output, we don't have a data file, right? So if I got a timer, then I would use what? 4. Right? This is the what? Plot number. This would be the word number. If you have a multi-word input module. If you don't have a multi-word input module, then you don't have to log. You're not explicit, right? Okay? This would be the bit address. If I wanted to address a whole word, what would I do? Start like that. Which is very good. We'll show you all a little bit of that too. Fixed PLCs, your slot numbers are going to be what? Going to be 0, right? The data file's understood, so this is kind of misleading too. The guy said, we put her out there. This would be T, right? And then it might be what, 4. There's no slot number for timers, right? Maybe a word number, right? I could get to the accumulator or something like that. But what's nice about your timers is we're going to give these things names. We'll have them get timers in town. So these two things right here will have a name. So we got a file in there called, we got a register called accumulator. We don't have to, that it's a word, it's a whole word. So we don't have to address it by law. By a number, we'll address it by name. We'll find out on the count. And that's it. So let's look and see what labs we're going to do. And they do have lab books downstairs? So right now we're working on what lab? 6-2. I think it's got 2 activities in it, right? Mm-hmm. So guys, this will be the last night I can give y'all out labs. You got to buy your lab books since they're down there. I cannot keep doing this. They're gonna. So 6-2, what's 6-4?
6-4 is full contact.
Yeah, so that's this guy right here, right?
Mm-hmm.
So is there any programming in this? Looks like it's all homework. So I'll look it over for me.
It does say in activity 1 to create it. Okay.
Oh, it does? Okay. So yeah, so activity 1, so this is program, right?
And activity 2.
And activity 2? Okay. So we're ready to do that. Then the next one I have is 6-6. Are these going in order?
Did we do 6-3?
I don't know. That's what this is. Just what I have. I don't have a lab book, guys. I got the old lab book.
6-3 was next up programming a PLC station.
What's that? Yeah, this I don't have a lab. I don't have one of the lab books.
And that one also says.
No, what? Now, what you need to look at. So the lab book's the same. We're okay. So 6-2, right? This is a lab assignment. Then I look at 6-3. What's at the top of there? Logic Pro. It's the same lab, but it's done on Logic Pro. We're not going to do that.
Oh, okay.
Okay. So anything that says Logic Pro, so we're going to skip over 6-3. The lab book's the same, even they don't give you log. 6-4. We can do 6-4. 6-5 is a Logic Pro. And 6-6. I have 6-6 up there. So these are right. Well, let's work on all the 6s. What's 7? Okay. So if you don't have these tonight, I can run them off one at a time for you. I can't run off all of them. What are you gonna have to do, guys? You got to buy your lab book, right?